Thank you for tuning in to the first part of Rocking Reservoir Waves lecture series. The Rock Physics Guided Machine Learning will comprise of 3 episodes that takes you into the fascinating world of deep machine learning for reservoir characterization, where our reservoir expert, Jyoti Malik, will unravel the secret hidden beneath the surface and embark on a captivating journey through the intricate world of integrating rock physics with machine learning. A brief background on Jyoti. She has over 10 years of working experience as QI geophysicist and has worked on a wide range of basins in India, Brazil, Pakistan, and Australia. An expert in integrating multidisciplinary data using deterministic and geostatistical inversion for reservoir evaluation and assessment. She has vast knowledge in seismic reservoir characterization and rock physics-driven machine learning, and been sharing them with the geoscience community through public workshops, societal conferences, trainings, and projects implementations. Hello, Jyoti. Welcome to the show. How are you doing?
Hi, Ayan, and thank you for the warm welcome. I'm doing well, thank you.
Now, Jyoti, let's talk about the buzzword of this decade: artificial intelligence, machine learning, and deep learning. Can you explain machine learning in simpler words and later throw some light on deep learning as well?
Sure, Ayan. Let's start this whole topic from artificial intelligence, machine learning, and deep learning, because we are listening to these words very often. Well, artificial intelligence, widely known as AI, is intelligence demonstrated by machines as opposed to intelligence of humans and other animals. For example, speech recognition, computer vision, translation between different languages, etc. And machine learning is a branch of artificial intelligence and computer science which focuses on the use of data and algorithms to imitate the way that humans learn and gradually improving its accuracy. Deep learning is a part of a broader family of machine learning methods based on artificial neural networks with representation learning. So these are the simple explanation for these different terms, or I would say the definition for these different terms. But let's try to understand this AI, ML, and deep learning with taking a simple example. So if I say that if I know the weight and height of few family members, I can find a relationship between heights and weights. And if I know the height of another family member, then by using the previous relationship, I can predict the weight of this another family member. Now you see, the accuracy of my prediction depends upon how many data points I used for building that relationship. Let's say that if I had data from only 3 family members, their weight and height, we know that our relationship is not robust. However, if I have the data point of, let's say, 100 family members, now the relationship we know that the one we are building is robust, and my confidence in predicting the weight of another family member given the height will be much higher. So the idea is, more the data we use for machine learning, better the relationship and thereby better the prediction.
This sounds interesting. So I am wondering how this machine learning started. Can you give a brief history of machine learning?
You see, Ayan, machine learning is not a new concept. In fact, I would say that within Hampson Russell, we have been using machine learning in reservoir characterization since late 90s. In fact, it initially started with building multilinear relationships between several properties, and then around early 2000, traditional neural networks with one hidden layer, like probabilistic neural network or radial basis, etc., they came into picture. And during last few years, due to significant improvement in hardware and computational strength, deep learning has rapidly evolved.
Whoa, I didn't know we have been using machine learning all this while. Jyoti, can you relate this machine learning to oil and gas, specifically reservoir characterization?
Certainly, Ayan. This entire workflow that I explained before, it can be applied to the oil and gas industry as well. In fact, machine learning in oil and gas has widely been used in seismic processing and traditional interpretation. For example, if we talk about structural interpretation, we pick a structure on few locations and then interpolate. This interpolation has got a machine learning algorithm behind it. And we have dramatically improved these algorithms over a period of time because we train these networks on widely available seismic data. There is no dearth of seismic data in oil and gas industry. Hence, the data amount is so abundant. So we have been improving on these algorithms over a period of time. In a similar way, we have been using this machine learning in seismic processing as well, like the first arrival picking. And you will see that most of the time we got even 5th generation or 10th generation algorithms for such purposes. Similarly, in reservoir characterization as well, we have been using machine learning for a while now. You see in reservoir characterization, as we are integrating the wells and the seismic data to derive a more robust model of the subsurface in terms of elastic properties or reservoir properties. So if I try to explain the use of machine learning in a very simple example, mathematically, let's say that in our field we got 3 wells, and within those 3 wells we have interpreted porosity as well as a 3D seismic data. So if my objective is to generate a 3D model of porosity for the subsurface, then what I need to do? I would need to establish a relationship between the porosity and the seismic data at well location. This is the only information that I have at the well location. So I will build a relationship over there, and this relationship can be either linear or non-linear. We know that. So let's say that we talk about a simple linear relationship. Then I would fit in a linear regression between porosity and seismic amplitude using the data points from these 3 wells. And this is what we call training. If I blind one of the well, then I can also do a validation about my training as well. And after this training, then we will apply this relationship to predict porosity away from the well locations. So this is how we will be predicting a 3D model of the porosity by building the relationship between seismic amplitude and porosity at the well locations, and thereby applying that relationship away from the well location. Now you see, the relationship can be linear or non-linear. For the linear, we are using a simple linear regression or a multilinear regression, whereas for the non-linear relationship, we will use neural network for the training and the validation purpose. If I talk about neural network traditionally it used to have one layer of input, one layer of processing, that is the hidden layer, and one output layer. This hidden layer, it has got several neurons, and the input to each neuron in this hidden layer is coming from the input layer. There's a weight, bias, and an activation function. After we process within this hidden layer, the output is generated, and this is what we call as the output layer or the final output that we are trying to predict. Traditionally, this kind of neural network had only one hidden layer for processing. However, in the recent times, due to the advancement of computational power, we are talking about deep machine learning or deep neural network, which has got multiple hidden layers. And this is what we are saying deep ML or deep machine learning or deep artificial intelligence. But you see, here comes the challenge. We usually do not have enough amount of well data in the early stage of our field life cycle in order to train a deep neural network or a deep machine learning algorithm for reservoir characterization. And that's the biggest challenge.
Oh, this challenge that you just spoke about brings another question to my mind. Can you explain inputs for machine learning? And can you talk about the amount of input data requirement for machine learning? And then maybe later we will discuss this challenge in detail.
Right, Anne. Let me try to explain this with a simple machine learning like the multilinear regression, and we will take the same example as we discussed about talking about 3 wells. But this time, let's try to make the data availability more simple so that it becomes easier for us to understand. So in these 3 wells, let's say I talk about the acoustic impedance and the porosity. So in 3D, I got my acoustic impedance coming from seismic inversion, and at the well locations, in addition to acoustic impedance, I also have my porosity interpreted by a petrophysicist. Now you see, I want to transform this acoustic impedance into porosity. And we know that porosity has a relationship with acoustic impedance. So to begin with, I have measured porosity values at these 3 wells. I also have the acoustic impedance at these 3 wells. So I will be using this information for the training, and this information at the well location is what we call as a labeled data. So at the well location, I build a relationship. It can be linear or non-linear between porosity and acoustic impedance. This labeled data is what we call as an input for the machine learning. And you can see that we are building a statistical relationship between the well property, which is porosity and impedance. And theoretically, we know very well that more the number of data points available with us, better will be the statistical relationship. So your labeled data is the input for the machine learning algorithm.
This is quite intriguing. Jyoti, I've always wondered that in reservoir characterization, we are estimating 3D elastic models of the surface, whereas in machine learning, by building the relationship, which you just explained, we can predict any property. So my question is, how different is seismic inversion from machine learning? Are these two methods used to predict the same properties or different properties?
That's a very good question, Ayan. And in fact, I have also been thinking about it. So let's start with seismic inversion, because traditionally we have been doing seismic inversion. So seismic inversion, it integrates wells and seismic data to estimate elastic properties of the subsurface. Let's say that if I am doing a AVO seismic inversion, and if I use Aki and Richards equation, or it's some approximation, let's say Fatty's equation. So seismic inversion, basically, if you see, has a theory behind it. And we can classify seismic inversion as a theory-based method. And the output from the inversion process will always be an elastic property. It can be a single elastic property, it can be multiple elastic properties, depending upon whether we are doing a post-stack inversion or a AVO seismic inversion. Whereas machine learning in reservoir characterization is traditionally applied after seismic inversion. We use machine learning to transform the inverted results into reservoir properties like porosity, saturation, or volume of clay. Although we could use machine learning to predict elastic properties as well. However, we usually don't do that because we already have sophisticated theory-based method to estimate those elastic models of the subsurface. So if I answer your question, inversion will always give us elastic properties. Machine learning can give us any kind of property that we are interested in, but most of the time we are interested in reservoir properties from the machine learning rather than the elastic properties.
Jyoti, this is interesting. However, I think every coin has two sides, right? We have discussed the strength of machine learning. Now I wonder about the limitations, which you briefly mentioned before. Can you talk about the limitations of machine learning used in reservoir characterization?
Like I just explained, and we required label data to build statistical relationships, and that's the input. And more the amount of label data available, the more robust is the statistical relationship. And this is the challenge for us in reservoir characterization, especially while using deep machine learning, where we require a large amount of label data. And usually we do not have large number of wells in the field, or even if the wells are available, we do not have the properties recorded or the interpretation as per our objective. Let's say I'm interested in porosity. So it may so happen that few of the wells have been drilled in the field which are very old. Either they do not have interpreted porosity, or initially the interpretation was carried out for a particular shallow zone of interest, and now over a period of time our interest has shifted to a deeper reservoir. So you see that we have a well, but we do not have the property in the well which can be used in machine learning. So practically, it's like kind of that we haven't drilled a well for that particular reservoir interval. And this is the reason why we are limited in terms of our labeled data, and hence limited in terms of the application of machine learning to conventional neural networks, and we haven't been able to use much of the deep neural networks inside reservoir characterization.
Thank you, Jyoti. This explains why people always talk about large data requirement for training any algorithm. Jyoti, is there a way to overcome this limitation and use deep machine learning in reservoir characterization?
And that's the question, talk of the town. Very interesting. In fact, people came out with various ideas. Industry has been working on this side. And if I talk about very simple idea, one is that I can randomly generate synthetic wells by just using the statistics of the wells present in the area. So that can be one way. But you see that this kind of approach can be very biased depending upon the kind of signature that has been recorded in the drilled wells. Let's say that if I have 4 or 5 wells and most of the wells are drilled in the channel sands, so in this case, I do not have enough amount of data representing the statistics of non-reservoir. And you see, if I'm doing simulation using this kind of a method, then this could introduce bias in my analysis or in my simulation. So this is the reason that there is a need to bring together some theory-based method to overcome this data limitation. We cannot do just simple simulation looking at the statistics of the drilled wells. And our researchers, Dan Hampson and John Downton together, recently they have come up with an idea of integrating rock physics model, RPM, to generate a synthetic catalog which becomes the representative data for the field. So that's another idea that we have come up with and incorporated within Hampson Russell.
Oh, wow. Synthetic catalog from rock physics modeling. This actually sounds very interesting and different. I already have a couple of questions in my mind right now, like how we are integrating rock physics model, what are its advantages over traditional methods of simulation, which deep machine learning algorithm are we using and why? However, I will park these questions for the next episode. Thank you so much for your time, Jyoti.
Thank you, Ayan. Thank you so much.
And for our listeners, stay tuned and we will take you through this interesting world of rock physics guided machine learning and see how it improves our interpretation over traditional methods. Thank you so much for listening to this podcast, and I hope you have enjoyed listening to us. If you have questions or topics you'd like us to cover, feel free to reach out via our website or social media channels. Until next time, keep embracing the geological wonders and keep exploring.